The second thing about billiards that's very sweet is that not only dynamics is trivial, tuk, 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 but stability is trivial. As I leave a wall of the billiard and I move on in the world, I start here and I move in a two-dimensional plane, four-dimensional phase space. And I want to emphasize that there are coordinates that we use. We are using x1 and x2 coordinates, but the Dr. Strangelove coordinates are the smart ones, the co-moving ones. As I move here, what kind of perturbations can I do? One is I can just shift the trajectory orthogonal to it, because if I move along the trajectory, nothing interesting happens. So the only orthogonal dimension is important. So I can define a local coordinate dz. So it's a 90-degree. That's a transformation in position space. What is momentum? We wrote our position in 4 dimensions as for coordinates. Know that p magnitude is 1 in our convention. So this is a unit vector. So the only thing that defines this vector is its angle in my coordinate frame. So there's some angle here in my local coordinates. This is q1, q2, sine of this angle, cosine of this angle. Momentum has to do with angle. The only change of the momentum has to be angular change, because its magnitude cannot change. The other natural coordinate is to change the angle. That's an acceleration, change of the momentum, delta. And this is translation. So now let's see what happens to the particle. As long as particle is moving freely, there are no accelerations on it. So the only thing we can study is how it moves transversally. The moment it experiences a potential, here potential is 0, here potential is infinity, then there is no translation. Everything happens instantaneously in space, but there is a large acceleration because momentum gets shifted by a finite amount. So let's just do first the free flight and study what happens to small perturbations. That'll give us the Jacobians. So free flight, the Hamilton equations for this particle, time change of q is and time change of momentum, acceleration is minus . In free flight, Hamilton equations are very simple. dz, this transverse coordinate, is just proportional to the momentum change. Why is that? Because if I decide to move at an angle to this line, my distance from the line will be changing proportional to the time. And dt of the momentum, d phi, is 0 because there is no acceleration. So this I can integrate, and I get a formula from going from here to there in the free flight. I get that dz n minus 1 Alex. So what I mean by this, I had some transverse displacement along this direction. And by the time I hit the disk, or infinitesimally before I hit the disk, I've flown this length, which I know how to compute. And the growth of the distance is just proportional to the time. But there are no accelerations, so the momentum doesn't change. So this is a situation, infinitesimal in time before I actually hit the disk. Now, infinitesimally, after I've hit the disk, which will be pluses rather than minuses, I'm going in a totally different way. So now the Jacobian, this is a linear equation, and Jacobian associated with the translation, which is 1, 1, 0. So this is the deformation of the neighborhood in a free flight. Jacobian is just derivatives of this, partial derivatives, and this gives me 1. This gives me 1, doesn't depend on z, so I get 0, and here I just get the time of flight. So here is an analytic formula for Jacobian, and we already know it because the only thing we have to compute is this distance between the two disks, and we did this. All I'm saying is if I'm going at a little angle, time till later, the distance will be proportional to the flight because we're just separating it uniformly. But that says Jacobian is extremely simple. So now what happens at reflection, you can think of it like what would happen if I shine flashlight on the edge of this disk. So what happens is that if I'm coming in here and my neighbor is coming, delta z transformed and maybe minus delta z, just to make it look like. What will happen is this one will deflect like that, that one will deflect like that. So because I'm looking at the mirror, what will happen, it'll spread out. What it cares about is this footprint here. So if I hit it straight on, delta z will not change. And if I hit it at any other angle, it won't change either, right? Because nothing happens in the distance. The only change is in angle, which is acceleration. If I hit it very close to this grazing point, then I'll have a huge effect. You know, the thing that is grazed goes straight, but the one that's here goes at a big angle. So what I really care about is the angle theta. So let me write it. So remember, this is my impact angle here. And this thing that my dz is reflecting from of the order dz before the reflection minus all interval dz over cosine. So when theta is here, so bouncing exactly back, theta is pi, this is 1, and the interval is the same as dz, but as I approach the edge, this gets very stretched out by this cosine theta. So that's what this interval becomes. And now I don't have a quick way to explain the angles, so that I hope you will draw at home and maybe give me a nice drawing how to explain the angle. But if you were moving, here is a delta theta angle before. If this is a flat plane, this delta theta will not change because everybody is going to reflect the same angle. If it's a very small thing, it's changed hugely because a nearby trajectory will spread out. So it really cares about this curvature. And the formula is true for anything that locally can be thought of. Circles have local curvature, so we'll call this rho of n. What happens at this instant is that this distance doesn't change. This is instantaneous. But there is a reflection because, if I was going here and I go out, what was my right now becomes my left. So there's a minus sign here. I experience an acceleration. So delta theta after the acceleration, again, it's minus delta theta before. This comes from reflection. But now you get a term which is minus 2 over rho n cosine. I can't explain 2 here, but 1 over rho must be here because the smaller the disk, the more defocusing it is. And cosine of the impact angle must be here because the more to the grazing I go, the smaller this angle should be, and the more spreading, more acceleration I should get. And now that written as Jacobian gives me Jacobian for one iteration in reflection, which is 1, 1, because these two guys are there. But now there is a minus, minus, so there is a minus in front. Where Rn is this quantity. So just by looking at the co-moving frame, we get extremely simple and very intuitive formula of what the dynamics is. It tells me that if I start someplace on a billiard, whatever the billiard is, I start on it with some velocity and some position. The first algorithm told me how I compute the next velocity, but in the co-moving frame of it, I also just get a Jacobian. So Jacobian for one iteration. So what happens if I perturb transversely or angularly around this trajectory? The Jacobian for one iteration is a first fly freely time t, and this is just a matrix, and then I reflect. And so the first algorithm told you how to compute it. Once you compute it, you know all the numbers, because you know all these angles, radii, and time flights. So you know the Jacobians. So once you compute the orbit, you know its stability. It's a simple, no extra computation, you just substitute in this. Suppose you have two disks and you're trying to play a very good pinball game by bouncing around these two disks. You go this way and that way. So mathematically you can do it. If it's on a line connecting the centers, this will always go forever. But you can now analytically compute its stability. So you can compute that Jacobian of this prime orbit is thing that cares about the flight time. So this part is having to do with accelerations and potentials, and this one has to do with free motion. And Jacobian is just product of those things. Now, you can immediately check the determinant of Jacobian is determinant of these two guys. But when you look at them, they have one on diagonal, 0 here, so this is 1. And because there is a reflection, there's actually -1. But basically, the volume is being preserved, phase space volume. So that's something you know from mechanics. The way I want to use this toy model is by playing with it and showing, see what are we trying to do. First we looked at individual trajectories, then we looked at little neighborhoods of trajectories, these are Jacobians. Now we want to describe everything. So what are all possible motions? So we want to classify them. For this problem we'll be able to classify them totally. We'll have to produce a complete list of every possible thing that can happen in 3 billiard. That's called partitioning of state space. So every part of state space will have a name. And that you will really understand, you'll be able to do it.